Hi apes. Today we're taking a look at Unit 6 Part 3. So we're going to pick up where we left off with oil. So last time we talked about how oil is formed, where it's found. And so now what we're going to do is talk about what we do when it is found. So once you find your spot for oil, we do have to pump it out of the ground and then go through a series of processing. So when we pump it out of the ground, typically what we'll do is we'll first start with allowing it to come up out of its own pressure, which will take care of about 10% of that oil. And then we do have to help force that oil out. So the way that we typically do that is up here is we will inject a fluid down into that reservoir rock where the oil is stored, and that will force the oil out. Now, enhanced recovery, what we do with enhanced recovery is you can then put steam down in there. Now, once we find an oil deposit, we're never going to get 100% of that oil out. And so this is where technology keeps improving about ways to get more and more of that oil out. So when we talk about running out of oil, one of the things is that technology is going to continue to improve and allow us to go back to some of these oil deposits and remove some of the oil that's left behind. But it doesn't just come out of the ground on its own. So for our underground deposits, we do have to have another well that we build to inject fluid down into there to allow that oil to be forced out. Now, once we do get the oil out, it is a crude oil. So this is not an oil that is ready to be used in any way, shape, or form. So we do have to go through a processing. So I'm going to allow a video to explain this process because what we use is a process called fractional distillation. Once you have your crude oil, you can get so many different products from oil, which is why it's such a key component in our infrastructure around the world. So you're going to use the boiling point differences of the various components of crude oil in order to separate it out to the different types of products that we get from oil.
In this video, you will learn how fractional distillation separates crude oil into useful fractions. Crude oil is the term used to describe unprocessed oil. That is oil that has been taken directly out of the ground, either on land or under the sea. It is an exceptionally valuable resource. It provides us with a great number of hydrocarbons, some of which are useful as fuels, and others are used in the manufacture of many different chemicals and even plastics. However, in the raw form as crude oil, it can be a viscous, dark-coloured tar-like consistency, and the different fractions of hydrocarbons must be separated by fractional distillation for them to be useful. Before we understand how fractional distillation works, we should be clear that crude oil is a mixture of hydrocarbons with different chain lengths, some being short molecules and some being very long. Intermolecular forces act between molecules, and the longer the molecule, the greater the intermolecular force. As you can see here, the small molecules have weaker intermolecular forces, and so will require less energy to break them apart and turn them into a gas. They have a lower boiling point. The longer molecules have greater intermolecular forces. More energy is required, a higher temperature will be needed to evaporate these molecules. They have a higher boiling point. Now we understand how chain length is related to the boiling point of a molecule. Let us look at how this method works. As you can see, crude oil is heated up to a high temperature outside of the fractionating column. The hot crude oil, now mostly in vapour form, is pumped into the column. The column has a heat gradient and is very hot at the bottom, going cooler as we move up to the top. Even at the very bottom of the column, where the temperature is still high, some long chain molecules with high boiling points begin to condense back into a liquid. These are collected at the bottom of the column. The rest of the molecules start to rise up the column, making their way through bubble caps in each tray. The bubble caps slow down the rate of the rising vapour, and eventually the vapours get too cool, condense, and are collected as liquids in the trays. Small molecules have low boiling points and so condense much higher in the column where the temperature is cooler still. As you can see, hydrocarbons with similar boiling points are collected in the same tray, and this is why they are known as fractions. They are mixtures of hydrocarbons with similar boiling points. Each fraction has some important uses. Some examples of fractions are petrol, useful as a fuel for cars; naphtha, used in the manufacture of chemicals; kerosene as aircraft fuel; diesel oil, used as fuels for vans, cars and lorries; and bitumen, a mixture of large chain hydrocarbons used to lay roads. Now, at the end of this video, you should understand that crude oil is a mixture of important hydrocarbons, and that fractional distillation is the method used to separate crude oil into useful fractions with similar boiling point. You should understand that small chain molecules are collected at the top of the column since they have lower boiling points, and larger chain molecules are collected further down the column as these have higher boiling points.
So hopefully that video did a good job of explaining this process of fractional distillation, of taking advantage of that difference in boiling points to separate it out into components, because we really do get so many products from oil. Most of the energy component of oil goes into our transportation, so things like gas and oil for our cars, planes, and trucks. But also we get an incredible amount of products from oil. We get the components that make plastic, polyester. There's not many components or not many artificial products that don't contain some version of fossil fuel in them. So that is one of the key components of why we continue to look for oil sources. Another thing that it is relatively easy to transport from the sources of our oil to the refineries where we distillate, where we go through the distillation process. You can use these pipelines, or you can transport it by boat. So it is relatively easy and safe to transport, and it is a little bit cleaner than coal. But we do still have the same type of problems with oil, in that it does create CO2, SO2, it does have metal components that are released when it's combusted, and then you have the added layer of oil spills. So we will get to more of the problems with oil spills when we talk about water pollution, but that is one of our downsides, because oftentimes we are mining for oil underwater. And if there are problems with the mining process underwater, that's going to release oil into our waterways. Or we can have pipelines like this that might spring a leak, and based on the biomes that they're going through, one of our biggest pipelines comes from Canada up through this very fragile area that takes a long time to recover from something like an oil spill. So we have pipelines that come from the oil fields in Canada and go down to our refineries in Illinois and Oklahoma. So definitely oil spills are another layer of problem with this component. Now, natural gas is often found with oil, and natural gas is an up-and-coming source of energy for electricity in particular. So more and more attention is getting paid to natural gas. Now, up here you can see some of our natural gas reserves, that Russia, Iran, and Qatar are our top countries for natural gas. So again, some of our Middle Eastern countries, because it is often found with oil. Now, when we talk about natural gas, most of the time what we're referring to is methane, or CH4. So that's most of our components of our natural gas when we refer to it. Now, for our other types, you might have ethane, propane, or butane, or hydrogen sulfide. Now, with natural gas, the reason why it's getting a lot more attention is because it is cleaner and more efficient than coal or oil. So because it is just CH4, you don't have the same types of pollutants that you do with coal and oil. So most of the uses of this are for electricity, but also you see some industrial uses. Some of you might have household natural gas. If you turn on your stove and you see a flame, that means that you have natural gas feeding energy into your home. Often that's tied to your hot water heater and or your stove. Also, it's used for fertilizers. and we can liquefy natural gas to make it like propane. And the main way we get to natural gas is with fracking. So fracking is a method that we are going deep into the crust, and you go horizontal once you find your source rock. Now, fracking, that term, refers to fracturing of rocks, that we use explosives underground to break rock to allow the gas that's trapped in the rock itself to be released and go through a pipe. So I'm going to go through a video that shows how this fracking process occurs so you can get a better visualization of the scale and the method.
Deep underground lie stores of once inaccessible natural gas. This gas was likely formed over millions of years as layers of decaying organisms were exposed to intense heat and pressure under the Earth's crust. There's a technology called hydraulic fracturing, or fracking, that can extract this natural gas, potentially powering us for decades to come. So how does fracking work, and why is it a source of such heated controversy? A fracking site can be anywhere with natural gas, from a remote desert to several hundred feet from your backyard. It starts out with a long vertical hole, known as a well bore, drilled down through layers of sediment. When the well reaches 2,500 to 3,000 meters, it's at its kickoff point, where it can begin the process of horizontal drilling. It turns 90 degrees and extends horizontally for about 1.5 kilometers through a compressed black layer called the shale rock formation. A specialized perforating gun is then lowered and fired, creating a series of small inch-long holes that burst through the well's casing into the rock layer. About 3 to 4 months after the initial drilling, the well is ready for fracking to begin. Fracking fluid is pumped down into the well at a pressure so high it cracks the shale rock, creating fractures through which the trapped gas and oil can escape. The fluid itself is more than 90% water. The rest is made up of concentrated chemical additives. These vary depending on the specific characteristics of the fracking site, but usually fall into 3 categories. Acids for clearing debris and dissolving minerals, friction-reducing compounds to create a slippery form of water known as slick water, and disinfectant to prevent bacteria growth. Sand or clay is also mixed into the water to prop open the fissures so the gas and oil can keep leaking out even after the pressure is released. It's estimated that all of fracking's intense pumping and flushing uses an average of 3 to 6 million gallons of water per well. That's actually not a lot compared to agriculture, power plants, or even golf course maintenance, but it can have a notable impact on local water supply. And disposing of used fracking water is also an issue. Along with the trapped gas that's pumped up to the surface, millions of gallons of flowback liquid come gushing up. This liquid, containing contaminants like radioactive material, salts, heavy metals, and hydrocarbons, needs to be stored and disposed of. That's usually done in pits on site, in deep wells, or off-site at water treatment facilities. Another option is to recycle the flowback liquid, but the recycling process can actually increase levels of contamination since the water is more toxic with each use. Wells are typically encased in steel and cement to prevent contaminants from leaking into groundwater, but any negligence or fracking-related accidents can have devastating effects. Fracturing directly into underground water, hazardous underground seepage and leakage, and inadequate treatment and disposal of highly toxic wastewater can potentially contaminate drinking water around a fracking site. There's also concern about the threat of earthquakes and damaged infrastructure from pressure and wastewater injection. Links between fracking and increased seismic activity leave unresolved questions about long-term pressure imbalances that might be happening deep beneath our feet. Fracking's biggest controversy, though, is happening above the ground. The general consensus is that burning natural gas is better for the environment than burning coal, since the gas collected from fracking emits only half the carbon dioxide as coal per unit of energy. The pollution caused by the fracking itself, though, isn't negligible. Methane that leaks out during the drilling and pumping process is many times more potent than carbon dioxide as a greenhouse gas. Some scientists argue that methane eventually dissipates, so has a relatively low long-term impact. But a greater question hangs in the air. Does fracking take time, money, and research away from the development of cleaner, renewable energy sources? Natural gas is non-renewable, and the short-run economic interests supporting fracking may fall short in the face of global climate change. Experts are still examining fracking's overarching effects. Although modern fracking has been around since the 1940s, it's boomed in the last few decades as other sources of natural gas decrease, the costs of non-renewable energies rise, and cutting-edge technologies make it so accessible. But many countries and regions have already banned fracking in response to environmental concerns. It's undeniable that fracking has reshaped the energy landscape around the world. But for what long-term benefit, and at what cost?
So that does a good job of showing the process of fracking and also talking about some of the downsides of it with the incredible water use, the amount of water pollution that's created, the seismic problems that are created, and what that means is that it forms earthquakes because of the instability potentially and the explosions underground. And then finally, that methane itself is a greenhouse gas and much more powerful than CO2. But we are seeing more and more of this because the demand for natural gas is going up because it is slightly cleaner than CO2. Than coal. It produces less CO2. And because we're finding more and more of these deposits in our shale rock. So that leads us to our final type of oil source, which are oil sands, oil shale, and some of these alternative types of fossil fuels. So we typically get to these types of the oil shale and natural gas through fracking. And this diagram down here will show us that shale is a type of rock. It forms in these horizontal seams. And so we can access this natural gas through there, but also oil. So we're starting to get to the point now we have a tremendous amount of these oil shale deposits around the United States, particularly in our Midwest and into Texas, as well as up in Pennsylvania and into West Virginia. So with these types of shale and light and tight oil, you get this through fracking. It's a lower quality oil, it's harder to get, but as technology changes and as the market changes, it makes these types of oil sources more and more viable. Now, where we saw this really turn in the market, how big of a role the market play is in Canada's oil sands. So because this is such a huge oil component on our world market now, I want to show a quick video that shows how oil sand is formed and mined in Canada.
Canada's oil sands are recovered using two main methods, drilling and mining. About 20% of the resource, known as bitumen, is found within 70 meters of the Earth's surface. These reserves, a mixture of bitumen and sand, are shallow and can be recovered through mining. Only 3% of the oil sands' total surface area can be mined. Oil sands mining is a three-stage process: mining, extraction, and tailings management. Typically, in mining operations, the oil sands are scooped up by large shovels and loaded into heavy haul trucks. The trucks deliver their load to a crusher, which breaks down the large clumps of bitumen and sand in preparation for transport. There are several methods of transport. One is hydrotransport. Water is added, and this mixture is sent to the extraction facility by pipeline. During extraction, the mixture is fed into an extraction vessel to be treated. Hot water is added, which helps separate the bitumen from the sand. Gravity pulls the sand to the bottom of the vessel while the bitumen floats. Sometimes the bitumen goes through a second separation process to improve the quality. The bitumen is removed as a froth and is now ready to be moved to an upgrader or sent via pipeline for export. Meanwhile, the mixture of sand and water at the bottom of the extraction vessel, also called tailings, is transferred to tailings ponds to settle and separate. As the solids settle out, the water on top is sent back to the mine to be heated and used again in extraction. Recycling water in this way reduces the amount of water needed for mining operations. All lands disturbed by oil sands mining operations, including tailings ponds, will be reclaimed to a self-sustaining landscape. Bitumen is a valuable resource that can be refined into transportation fuels such as gasoline, diesel, and jet fuel. It can also be used by petrochemical plants to create everyday products like cosmetics, textiles, plastics, and lightweight construction materials. Learn more at cap.ca.
So as we are starting to run out of some of our more traditional types of fossil fuels like coal and traditional oil, we are seeing a shift to these alternatives. The oil that's trapped in shale rock, natural gas, and then these oil sands. Now the oil sands in Canada are a tremendous amount of habitat destruction. The video talked about how it was formed and how it was mined, but to get to that layer of oil, that is a strip mining process where they have to strip away the top layer. And then with the processing of that oil, in order to separate the oil from the sediment itself, it's tremendous amount of water use. That's a lot of habitat destruction, that's a lot of water use and a lot of pollution before it even gets to the fractional distillation part to put it into those components. So it's a much dirtier oil than our traditional oil is. So we're seeing this shift in these types of fuel sources that we're using because of the decline in our traditional types. So next class, we're going to talk about our remaining non-renewable fuel source, which is nuclear, but this is moving away from fossil fuels. The reason why we call coal, oil, and natural gas fossil fuels is because these are plant material that was alive millions of years ago, and this process takes a very long time for the heat and pressure to convert it to these coal, oil, and natural gas. And the key thing to remember about these is that all three of these are non-renewable. We will not make any more coal, oil, or natural gas. So conserving what we have and finding alternatives is going to be key.